So starting our today's topic, so timber and fire, what is the real challenge in the design of practically any timber structures from all the structural engineers is basically fire design. So although in the last decade there's been a big increase in timber and then all the practical examples that we can see. So aesthetics, sustainability, prefabrication, and performance are just things that make timber highly attractive. But one thing that keep concern is actually the fire. So thankfully, the new Eurocode was published in September 2025 and superseded the version from 2004. The things that this version mainly brings are we have finally explicit rules for CLT fire design and CLT in general as a material. Also, in terms of fire, we have fire verification moves to more physics-based European Charring Model and effective cross sections. And importantly, now it now accounts for what happens when the fire protection falls off and charring accelerates. And that's exactly what my colleague will take you into detail. So thanks you again for joining this webinar. Please put your any questions or comments into the chat, and we'll cover them at the end. So yeah, thanks again, and over to you, Rasha.
Thank you for the intro, Marco. I will share my screen and start presenting the good morning, everyone. Welcome to the Spec Toolbox webinar series, and also thank you for making the time to join us. My name is Radov Bogojevic. I am structural engineer with 6-year experience in mass timber design, and I work in Spec Toolbox as technical sales representative as a member of product management team. Today, we are looking at something that quietly rewrote a big part of our job last autumn. It is the second generation of the Eurocode 5 fire standard, which was published last year of the 30th September of 2025. And for the first time, cross-laminated timber gets its own fire design rules inside the Eurocode. That's a genuinely really big deal, and it is what this session is about. Before we start, Mark also mentioned some of those things, the 3 quick notes before we start. So first is this session is recorded. The second, please drop your questions into the chat whenever they come up, and we will take them at the end. Third one, this webinar has 2 halves. We will spend the first half in the theory, and after that, I will open the Spec Toolbox app and run the CLT floor and the wall through the real project in our app. So let's start by looking what is the plan for us today. This is our agenda for today. The webinar is in 2 parts. Part 1 is the theory in 5 short steps. Step 1 is what is genuinely new in the 2025 standard compared with the 2004 edition. Step 2, the European Charring Model, which is the new way of calculating how timber burns. Step 3 is the effective cross-section method, which tells us how much strength is left after a fire. And step 4, protection fall-off time, which is now something you choose and justify. Step 5 is where the new rules start, because every method has its limits, which is worth knowing. The part 2 is the live demo. We will take a worked example, a mass timber residential building, and design a CLT floor and CLT wall in Spec Toolbox from start to finish. So let us begin with the part 1. This is section 1, the main changes between the 2025 standard and 2004 edition. So if you learn timber fire design at any point in the last 20 years, you learned it from a document that has now been replaced. So 20 years of practice is now changed. And let us start the story of how we got there and look at exactly what 2025 code changes. Here we can see the 20-year road to the second generation code. The point of this slide is simple. So we can see what was defined and what was not at each step along the way. In 2004 edition, the first Eurocode fire part was published. It gave us a method for solid timber and the glue lamp, but it did not mention the cross-laminated timber at all. That yes, that was fair enough at the time, because at 2004 CLT was not that, let's say, popular product, but through years CLT became the backbone of mass timber construction while the fire code stood still. The next code that we have in 2011, Austria added the national annex, the CLT fire rule, in the standard called ONORM B, and that was the first time CLT fire behavior was defined anywhere in the code. Everywhere else, designers relied on the handbooks, product approvals, and manufacturers' literature, and the result was a patchwork that differed from country to country. Then the official process caught up. A draft of the new standard circulated in 2023. The European Committee approved the final text in the July of 2025, and it was published on the 30th September of 2025, formally replacing the 2004 edition. So if you're designing the mass timber, this is the moment where you can go to 2025 edition and design the new code. Here we have the table with the rows of what was defined in 2004 edition, what was then defined in the ONORM B in 2011, and what is now defined in the 2025 edition. So starting with the CLT in scope. In 2004, CLT was not mentioned in the code, so designers simply borrowed the rules for glue lamp. In 2011, Austria wrote the first proper CLT rules, but only in the national annex. It was not in the Eurocode. In 2025, we finally have explicit European rules for CLT. The next one, the charring model, which is how we calculate the rate at which timber burns. In 2004, it was a single constant rate. In 2011, it became a step model with the different rates in different layers depending on the adhesive. And in 2025, it is the full phase-based European charring model. Now the key row, what happens when a charred layer falls off at the bond line. In 2004, the code was silent. In 2011, Austria let's say measured it. In 2025, it is written into the standard with the charring rate doubling at each bond line. Then the zero strength layer, it tells the same story. The old fixed value of 7 millimeters was later shown to be unsafe for CLT, so 2025 replaces it with proper tables. And protection fall of time, which is used to be an assumption, is now explicit design input. So we can see that every single row comes to the same question: what happened at the bond line? So in 2004, code was silent. In 2011, it was measured, and now in 2025, we have the exact code which we should follow for the design. Before we go deeper, here is the one-piece orientation of that the code's own outer stress. So the second generation Eurocodes all share the same three-level structure. More effort buys you the more accuracy, and you choose the level that fits your project. So we have level 1, which is defined in the chapter 6, the tabulated design data. Here you simply look things up. If your build-up matches a published assembly, you read off its rating with no calculation at all, and this is the fastest route and also the most conservative. The level 2, defined in the chapter 7, the simplified design methods. These are code-approved formulas in the main body of the standard. This is the everyday level, the one most of us will use for the time, and it is exactly what SpecToolbox automates. It is where we spend the most of our time today. Level 3, the chapter 8, the advanced design methods. This is the full thermal and structural simulation used when the geometry or the fire scenario is beyond what the simple methods cover. it requires validation, and it is usually where you and the fire engineer work together. So the physics underneath is the same at all three levels. You just pick the amount of effort that suits your job. And today's webinar will mostly rely in the chapters 6 and 7. That was the history and the big picture. Now we can get into the model itself. We'll go to the section 2, the European Charring Model, and we will look at the charring rates, how deep the char goes, and how the 2025 code treats CLT specifically. So the model rests on the two charring rates, and it is worth keeping them clearly apart. The first is the basic charring rate, written as the beta 0. This is a fixed property of the material. You read it straight from the table 5.7. So for softwood members, and that includes the CLT, it is the 0.65 millimeters per minute. It never changed because it is simply a property of the wood. The second is the notional charring rate, written as beta n. This is the rate that you actually design with. It is the basic rate adjusted for the gaps and the joints and for the protection situation using the code calls the K factors. The char depth itself is given by formula 5.1. It is simply the charring rate multiplied by time added up across each phase of the fire. The material rate is fixed. Everything that happens to it whenever that is gaps, protection, or fall-off happens through the K factors applied to the same basic rate. Here is the charring that runs in phases. So we have 5 of them. And which ones apply depends entirely on whether the surface starts out protected or unprotected. The phase 0 is encapsulated behind an intake fire protection system, so no charring happens at all. The phase 1 is the normal charring, and unprotected surface chars at the notional rate from the very first minute. Phase 2 is protected charring. This is the charring behind protection that is still in place, so the rate is slowed down. Phase 3 is the post-protection charring. The protection has now failed, and the hot, barely charred timber underneath chars at double rate. Phase 4 is consolidated. Once a full 25 millimeter char layer has rebuilt, the rate returns to normal. So the simple version to remember is this: a surface that starts unprotected just runs with the phase 1, and the surface that starts protected runs through the sequence 0, 2, 3, and 4. It will be shown later in the diagram. Now let us look at the K factors for the plane members. The plane members are a flat members, so that means CLT floors and ceilings, which char on one flat exposed face. The first is the KG, which is the gap factor. If the gaps are tight, which is normal for the face bonded CLT, then KG equals 1, and there is no penalty. Wider gaps cost you up to 20% more charring, so it is worth putting the tolerance in your specification. The second is the K2, which is the protection factor. This is the slowdown while an intake protection board is still doing job during the phase 2. You read it from the table 5.8 by board type and thickness. The third is the K3, the post-protection factor. So once the protection or the char layer falls away, K3 equals 2, and the timber chars at a double rate until it consolidates. So the pattern is straightforward, the basic rate stays the same throughout, and the K factors do all the work of adjusting it. Here is the chart that shows what happens when the bond line holds, meaning the glue stays intact and the char layer stays in place. On the left diagram is a member that starts unprotected. It is a single straight line and charring at the notional rate from minute 0 all the way through. On the right is a member that starts protected. It runs through the phases in order, encapsulated and protected, then post-protected, and then consolidated, governed by the 3 time points we will meet shortly. The thing to notice is this: the slope only changes when the protection situation changes. As long as the bond line holds, the char line crosses each bond line smoothly with no jump. That was regarding the charring model, and now we'll go. Now we'll turn what it means for the strength of the structure. This is the section 3, the effective cross-section method. The charring model told us how much wood is gone, and this method tells us how much usable strength is left, and we will work it through the CLT. The whole method comes down to the 3 steps. So char it, strip it, and verify what is left. Step 1 is char it. You run the charring model to find out how deep the char goes for the fire resistance time you need. The step 2 is strip it. On the top of the char, you remove a thin extra layer called zero strength layer. This is the wood just behind the char that is too hot to carry the load, so we conservatively treat it as gone as well. The step 3 is verified. You take the section that remains and you check it using normal, full strength properties. If it still carries the load, it passes. The elegant part is that this single method checks the structure directly using the same charring model with no separate heat calculation needed at this level. The zero strength layer used to be the simplest number in the whole method. In the 2004 edition, it was a flat 7 millimeters for everything, but that does not happen now. In the 2025 code, the zero strength layer depends on 3 things: which side is exposed, the position of the char front, and the layer you are in. For horizontal members, meaning floors, you read fixed values from table 7.4. For vertical members, meaning walls, you calculate the value layer by layer using the formula in the code. So the headline is this: the flat 7 millimeters of 2004 is now a history. The zero strength layer is now read or calculated properly for each side, each protection state, and each layer. It is fiddly by hand, which is exactly the kind of bookkeeping the toolbox handle for you, which we'll show later in our app. That was regarding the how we find the strength that remains. Now we look at the timing that drives it all. This is a section 4, protection fall of time as a design input. This section that most changes how you think, because the failure time of the protection is now a number you choose and justify. The whole protected sequence is governed by 3 points in time, and each one is calculated from the one before. So the first is the start of the charring. This is the moment charring begins behind the protection, which is the end of the phase 0. The second is the fall of time of the protection. This is the moment the protection fails and drops off. This is the design input that this whole section is about. The third is consolidation time. This is the moment the char layer reaches 25 millimeters and the rate returns to the unprotected value. The only idea to take away is this: the fall of time is now a design input. You choose it, you provide evidence for it, and you document it. It is no longer some assumption, it is a defined value. So where do those protection times come from? Each protective layer buys you a certain amount of time, and in this formula, which is defined in the 756, it prices every layer. So for each layer you take a basic protection time, adjust it with the position factor, add the extra time term, and correct it for the joints. You do this layer by layer, and then you add them all up. That total fits straight into the start of the charring and the fall of time from the previous slide. In other words, the boards and the insulation you specify translate directly into the timeline that covers charring. Change the buildup and the whole timeline will be moved. Now this is the picture of the initially protected and initially unprotected CLT, which you can see all the phases, and this, like a staircase says, is the signature for the CLT delamination. Also, it is something which was not defined in 2004 version. This is the last of our 4 core topics regarding the theoretical background. The section 5, it is a short but the important one. This is where the neurals stop. Every calibrated method has limits, and the responsible thing is to know them before your project finds them for you. So when does a project step outside the simple methods, and where do you go when it goes? When it does, the code gives you the 3 routes. The first one is the chapter 8, which we mentioned at the beginning, the advanced design methods. This is the full thermal and structural analysis for geometries, exposures, or materials that the simple methods do not cover. Validation is mandatory, so this is a rigorous part, not a shortcut. The second is the Annex A, the physically based fires. This lets you design for a real fire, including the cooling phase, and it counts the timber itself as the part of the fuel. This is where exposed timber design for a larger building is heading. And the third route is not close at all. It is a colleague, so the fire engineer, things like self-extinguishment, secondary flashover, and compartmentation are their expertise, and our structural calculation is one input to that wider conversation. So the simple path is wide and it covers the great majority of everyday CLT work, but now you know where its edges are. Before we go live, I just want to flag 2, neighboring topic that the new code opens up. The first is the connections. Connections for one of the weakest parts of the old code, and now the chapter 9 has been completely rebuilt. It now covers the fire resistance up to the 120 minutes. It applies to the usual laterally loaded connections, timber to timber and steel to timber with dowels, bolts, nails or screws. It gives you the 2 routes. You have the also tabulated data that you read straight off the table, and the calculation method for every day for everything else. Both are calibrated against the fire tests. This is also a neat rule for protected connections. If the protected survives and at least 20 minutes beyond the start of the charring, you only design for the shortfall. If it falls sooner, you add a time for a faster charring afterwards. The second neighboring topic is one of the exciting capabilities in the whole standard, designing for the entire fire, including the burnout. Everything so far has assumed the standard fire, which is a test curve that just keeps getting hotter and never cools down. It is a brilliant comparison test, but it is not a real fire. A real fire in a room heats up, reaches a peak, but then cools. Why does it matter for timber? Because exposed timber adds fuel to the fire. And NXA finally let us design for the real thing. We can use any temperature time curve, including the cooling phase, and we can demonstrate burnout, which means the point where the timber stops feeding the fire and it goes out of its own. This is the advanced territory, and it is squarely a conversation with your fire engineer, but it is now inside the Eurocode. And on that note, we can go, it is now inside the Eurocode. Now we can go to that was all for the theoretical background. Now we will go to the part 2, live in the spec toolbox. Now let's see how it works in the software. We will show our working example, a mass timber residential building, and we'll take the 2 real elements from this project, a CLT floor and a CLT wall, and run them through the new code live in our spec toolbox app. Let me set the scene for the work example, so the numbers have the later context. So this is a mass timber building in Amsterdam, in Netherlands. That means we will be working under the Eurocode 5 with the Netherlands national annex. The structure is as follows. So the floors we chose the 180 millimeters 5-layer CLT spanning a range of bays. So we have basically two span with different lengths. The beams are the glulam beams. The columns, we have also the glulam columns, and the CLT walls, which is in our interest to show here, is the 160 millimeter 5-layer with the 3 meters of height. For the fire design, we will focus on these two elements: the floor slab and the wall. Between them, they show both the floor and wall, and both exposed to the protected cases. So let us start with the floor design. Let's firstly define the loads on the floor. Fire design check at the fire limit states, so we need the right load combination. The floor buildup is a CLT with a 50 millimeter concrete screed on top. You can see the concrete topping and the acoustic underlay in the section on the right. On the top, we have the self-weight. We carry an additional dead load of 1 kilonewton per square meter for the finishes, and a live load of 3 kilonewton per square meter, which is the category in office areas in this case. In a fire, we design for the accidental combination where the live load is heavily reduced, so the load the chair flow actually has to carry is a good deal lower than design case. So the tailbox supplies that combination for us once we tell the occupancy. Now the floor itself, live in the software. So we have this 5-layer 180 millimeters, and we chose the CLT KLH with 4 plus 4 meter span. And the request is the 90 minutes, and we have the unprotected and exposed from the underside. Now we can show in the app how that works. Let me just switch to the screen in the app. So this is our spec toolbox app, and I already prepared these calculations for us. So this is our project, the 5-story building in Netherlands, and we'll go to the CLT floor design. So the first thing to define is the supplier. We can go with some custom supplier, or we can choose the existing ones that we have in the app. We chose the KLH supplier with the 160 millimeters 5-layer layup. As you can see on the dynamic picture on the right. For the design code, we chose the Eurocode. For the analytical method, we will choose the gamma method. For the 5-layer of the CLT, we can choose the national annex with Netherlands. Define the system strength factor. The load combinations will be taken from the national annex. Define the imposed load category. For the analysis data, we will use the one from our building, the 4 plus 4 meter span, and we will add the loads. So we have 1 kilonewton per square meter for the dead load and 3 kilonewtons per square meter for the live load. From the national annex, we will use the deflection data and also the vibration method from the Eurocode 2025 version. And here we can see just that vibration is the governing, but what is our interest today is to see how fire works. When we defined all this, we can go to the fire module. Here, so firstly, design factors, then the char data. So for the fire method, you will use the new 2025 version of the Eurocode. Fire performance criteria, we'll use load bearing. We don't have any insulation, but we have that option to also use the load bearing plus the insulation. the flexural case, you can use both top in the tension or in the compression, or the fire resistance level, which for each input you can go to the more information and see what is it about. So we will enter the 90 minutes basic char rate. We will use according to the Eurocode, and we have the option to select also the glue line integrity, is it maintained or not. That is the input that depends on the supplier also. So if we go back to the defining the CLT supplier, we can go to the more information, and here we can see if the glue line integrity fire is possible or not. So for the KLH supplier, it is possible on the request, so we are able to use the glue line integrity, and we can also see how it changes. So for example, we have the effective 74.5 millimeters. If we choose the not have the glue line integrity, it affects the results a lot. So in our case, we will use the glue line integrity maintained. We can here choose the exposed sides. So as said, it is exposed on the other side, it is unprotected, and also here we can use the joint type, the joint gap, and also the factors from the Eurocode. You can also quickly add the protection sides if there is. So you can add any layer, you can add the gypsum, the OSB, or the plywood, and you can see how the charring changes. In our example, we don't have any protection from below, so we'll exclude it. And we can go to the output summary. So here we can see that the shear in the fire and the bending in fire are passing the verification. All the output summary, the panel properties, bending check, rolling shear check. But what is interesting for us is now to see the charring. So in this charring tab, you can see all the charring rate factors. So the K2 factor, the K3 factor, the KG with all the formulas. So everything is presented, all the input data, also the charring rates for the unprotected and glue line integrity maintained. So we have the basing charring rate, which is 0.65 millimeter per minute, the zero strength layer depth. So we have the 90 minutes, which we entered. Also here, the tension side for the first layer, it is 7 millimeters. The tension side for other is 12 millimeters. So now we don't have fixed 7 millimeters everywhere. It changes. We can see everything what is used here. The design thickness. Now we can see the charred lamellas. So for the tension on the top side and for the compression of the top side. And here we can see what is the left of our profile, and you can also check in the dynamic images. So 85.5 is what is left untouched. Here you can see how all the layers burnt. And yeah, that's it for the charring. We can go to the another tab for the panel in fire. So here we calculate the stiffness for our new charred member. Then the annex, we can see all the parameters that is used, the loading in fire, so we can see all the load combinations and all the factors used, the analysis. So here we also have all the load combinations, and we can switch between them, see the shear force at each point, the bending moment also at each point with all combination used, the reaction forces also. You can switch between the load combinations, and designing fire. So we have the bending design of the charred member, the shear design, which we can see that is passing the verification. and that is our check for the CLT floor. You can also do the report. At the moment, only the detailed report is possible, so we can just quickly show how does that look. The summary report is not available at the moment, but will be available soon. So here we have generated the detailed report, and we can see all the inputs here, all the checks. So for the panel properties, bending check, all the information regarding the checks, the charring that we passed through. Now we can go to the CLT wall design. I will just switch back to the presentation to see what is the so going back to our presentation. We have the CLT wall design. So for the CLT wall, we have chosen the 5-layer 160 millimeter. Also CLT KLH, the height is 3 meters. Also we'll choose the Eurocode 5, the Netherlands national annex. The exposure is 90 minutes. It is unprotected. This is the external wall. It is unprotected and exposed from the interior sides, and we will check also these interior walls near the staircase, which is protected on one side and exposed on both sides. Now let's show this in the app. This is our external CLT wall. So we have all the inputs as for the CLT floor. We define the CLT supplier, the national annex, the loads on this wall, the method, and the geometry of the wall. Now we can go to the fire design. So we define also the fire method, the performance criteria, so it is also load bearing. We don't have the insulation. We can choose between the top in tension or the compression, the 90 minutes. It is exposed to the right face at this moment at just the interior face, and we don't have any protection yet. We'll show the protection in the next example for the interior wall. And now we can go to the charring. So we have the same, all the factors shown, the charring rate, the zero strength layer, also the design thickness, how much is left of the charred member, and we can see all the result of the panel, the annex, the load combinations, the eccentricity, the analysis also for the bending actions, and we can see all the calculations here. So the slenderness, the actual design, axial design, and the bending capacity. Now let's maybe switch to the internal CLT wall, where we can see the use protection and how the charring is happening when we have the protected side. So this wall is exposed on both sides, but it is protected only on the one side. So we can see here this we use the gypsum plasterboard type 3, and here we can see the charring and the zero strength layer. So the same, we define the method, all the inputs are the same. We have the 90 minutes, the glue line integrity maintained. We also use the CLT, so we are able to maintain it. You can also see how it changes in the results if we don't use the glue line integrity. So now we choose that side is exposed on both faces, and that is the good option in our software. You can choose which face is exposed, one or both. And here we defined the gypsum plasterboard. We use the 3 layer of the 12 millimeter thickness also for this. And now we can see the results. So we can see here that the fire is the governing one. If we check the, so the slenderness is 44% here, but in fire we have the 65%, which says that the fire is governing in the design of our wall. Now we can go to the charring rate. So we have the same charring rate factors, the charring rates, the zero strength layer. But what's interesting for us is to see this these protection times. Yes, here it is. Here we can see how it's calculated. So we have the gypsum plasterboard, the CLT of the layers, and we see all the protection times, starting of charring, and the failure time. Here also, so the fire from the right face, design thickness, what is left for the compression and the tension of the top side, and also we can check the panel in fire, also the annexes, the load code, also the eccentricity, the analysis in fire, and finally the calculation of the bending, axial, and the slenderness. So that's it from the examples from our app. I'll just go back to the presentation. So we've shown the example, and we can wrap it up. What is the process of calculating the fire for the floor and the walls? So this is the run sheet, and we can sort like 5 moves to make every time on whatever the element. So we define a floor or wall. That means the layup, the span, the loads, and the national annex. The second one is to pick the exposure and the protection, and pull the timing values from the code tables. The 3, we can toggle bond line integrity on and off and watch the phases resequence. That is the moment the staircase we saw earlier becomes real. The 4th step, review the charring layer by layer and the zero strength layer from the tables. And 5, verify the utilization across the range of fire ratings, and then compare your design options. And we can quickly recap what the toolbox just handled for us automatically. So it sequenced the charring rates layer by layer. It applied the zero strength layer from the tables, including the small layer rules that are so easy to miss by hand. It pulled the protection timing straight from the code tables, and it let us compare options, exposed versus protected versus a thicker panel, side by side in seconds. So here is a line to remember. You can bring the design intent. The toolbox carries the closed numbers, and you're already designing to the new code without rebuilding a single spreadsheet. And let us bring together. Here are the 5 things to take back to your desk. So 1, the 2025 standard replaces the 2004 edition. It is a new machinery, not a rebadge, and it is the first Eurocode with explicit CLT rules. The second, the European Charring Model runs charring in phases, and the doubling rule at bond lines finally makes the char fall of explicit. The third one, for CLT, the effective section is the char depth plus the zero strength layer, and that zero strength layer is now set by side, layer, and protection. So the flat 7 millimeters is history. Protection fall-off time is now a design input. You choose it, evident it, and document it. And 5, respect the calibration. So softwood, standard fire, tight gaps. Beyond that lie Chapter 8, Annex A, and your fire engineer. That brings us to the end. Thank you very much for your time today. Now I will take back to Marco, and we can see if you have any of the questions, and or we can wrap it up. Marco, up to you.
Thank you, Radovan. That was really great to see. So as Radovan mentioned, if you have any additional questions, feel free to drop it into your chat. We have a few comments and points that we'll cover now, but if you have any further things you would like to point out or address it, as I mentioned, just drop it into chat. So first thing is from Anthony that he mentioned that the new Eurocode is not enforced yet in the majority of European countries, and that's true. That's correct. We are now in transition period, so in some countries it's adopted or official, and in many others it's still in process, and national annex are not covering yet these new standards. But in case of fire and CLT in particular, it's still very valuable, as you probably noticed in what Radovan explained. There is no CLT provision, especially guidance around the fire in the previous standard. So even it's not yet fully official, it's still something that you can use, of course, with the guidance and being careful with authorities and the cross-check with other project documentation and references, since it's still something that will precisely give you some answers and clarity for your project. Going further, we also had one point from Manuel regarding the K factors, and the question is they supposed to be given from CLT suppliers? And also what happens with CLT joints when it comes to tolerances. So Philip already answered in terms of K factors, so only K2 is not presented in the table 5.8 from the new Eurocode, and that's something that should be provided from suppliers. Regarding tolerances and CLT joints in particular, that's something that you can manipulate with gap factor during the calculation, and in particular, that's also something that should be provided with or by suppliers and contractors, as that's something that should be encountered for the design itself, since gap factor is doing a lot of impact on the design itself. And we have another point from Rudis. So does the protection layer input account only the board lining protecting a CLT element, or can cavity insulation between timber studs also be included in the fire resistance calculation? Can the tool be used for a timber frame wall without any CLT layer? So at the moment, this calculator and what we currently support in our platform is only related to CLT. So we don't support yet any timber frame wall calculations for in case of fire. You can use a timber frame design module, but without fire at this stage. And also according to current version or old version of Eurocode. In terms of protection layer input for bone lining, so you have option for selecting different type of materials and layers for the protection, but I don't think cavities is something that we encounter at this stage. Definitely, what we cover is ability for calculate to use all the systems and protection layers defined in the Eurocode or the new Eurocode standard. So in accordance to that, we'll provide further guidance and also add other materials that will have specific guidance or instructions for use as a protection layer. But and we have another question from Jab. So do you have any possibility to calculate the multi-span system for timber concrete composite floors? Yes, so we have separate calculator for timber concrete composite floors, but Currently, it's only limited to single spans, so it's multi-span systems are not available at this stage. What we have in plan, though, is to add abilities for cantilevers in some midterm period for adding actually the multi-span is also something that is maybe question for suppliers and contractors in terms of what are the how effective those systems are when you have tension in and you need additional rebar in the top zone. So, but yeah, definitely something that we'll consider for the future editions. Yeah, if we have any further questions, we can also cover that as well. Yeah, another question from Manuel. So, new tool for hangers with different suppliers. Will fire check be included in it? Yes. So for some suppliers, we'll have straight away guidance for fire checks, but that won't be covered according to new Eurocode we are mentioning here today. That is something that will come in later stages and improvements. What we have now is only guidance based on the supplier recommendation and technical data sheets in terms of what is the suggested sections of members and beams that should be used for a specific fire rating systems. But detail calculation is something that will land in some of the future versions. Yeah. Thanks for the questions, by the way. They're all really good. And we might have another more. Yeah, we have another question from Ahmed. So does the fire checks also takes into consideration the effect of fire on connections like screws? At this stage, so in the module that we showed and Russia took it through, was mainly for it was actually for member design, so floors and walls. We also support beams and columns verification in case of fire, but actual design for the connection is in case of fire is not yet supported, although it's planned by our team. So in this stage, design for connections is only without fire design. But as I mentioned, is definitely something we'll looking into integrating all together as per new Eurocode standards has consideration for fire checks. Yeah, thanks everyone for your questions and for your time. Really great presentation, Radovan. And if you have any additional questions or thoughts or comments in terms of this webinar or presentation or calculators in general, feel free to reach out to us directly. We are looking forward to seeing you on the next episode. And yeah, have a great day, everyone.
Have a great day. Thanks for joining.
Bye.